Hello, everyone. So today we're going to continue our conversation of industrial chemistry to talk a little bit about petrochemical refining. So petrochemistry is essentially completely built on the found rock of oil. So in order to understand how we separate and process oil, we first have to have a good understanding of what oil is. So essentially, oil is essentially trapped hydrocarbon species in the liquid form that are found usually beneath impermeable rock, so they can't move up, but they're often located on top of impermeable rock or a water reservoir, so they can't exactly float down either. And so they're trapped in this steady space. There's almost always a little bit of natural gas in the area and the headspace above it, essentially evolving off of the oil, as oil will slowly decompose into natural gas under high heat. And in order to what we really care about, however, is going to be essentially the composition. So essentially, oil has a wide array of composition, but it's predominantly composed of carbon. This is the classic species, and it can be found in chains that go from methane all to C120 or even bigger. In there, and what often controls this composition is a variety of hydrogen percentages. The higher the hydrogen percentage, the more light species like methane we have, the lower the amount of hydrogen, the more heavy species we have. And then again, we can also have some impurities, mostly in the nature of sulfur, nitrogen, and oxygen. And the exact composition, so these exact percentages, are going to be highly dependent upon where the oil came from. And we're going to be trying to divide all of the various compositions of oil into two major categories. First, we can measure the density, and second, we can measure the impurities. So the classic description of oil is based on its density. And so this can be described using American Petroleum Institute gravity, which is essentially a slight modification of specific gravity. So again, the specific gravity is essentially the density of the oil divided by the density of the water. So it's essentially out of one. And then this can be corrected to the API gravity, where what we tend to see is that if you have a large API, this tends to indicate rather low specific gravities, and thus fairly light weights. And what makes these weights essentially lighter is that my species tends to be constituted much more of, have much more hydrogen present, and thus tends to form more of our small chain molecules, say C1s to C8s. And thus this is often called a light crude oil. And our light crude oil is essentially considered anything with a density of less than 0.85. So again, this would definitely float on top of water. However, as we work our way down the crudes, we tend to see things with densities a little bit closer to water. And this is essentially because I'm making more and more heavy chain molecules. By the time you get to extra heavy crudes, these are going to be very thick and viscous and are going to be much more dense than water. So some examples of some extra heavy crudes might be something such as the Canadian oil sands, which is almost entirely made of very heavy species. Now, one of the things we're really going to want to consider being chemists is which ones of these are going to be more valuable. And traditionally, chemists, we tend to like lighter molecules more. They're much more easy to chemically modify. So thus, the highest value tends to be put on the light crude. Similarly, we also need to regard impurity types. And usually our big metric of impurities is on sulfur. And one of the reasons why is because sulfur has a bad tendency to clog up engines and cause corrosion, as well as the classic, if you burn it, you can burn sulfur-rich oil, you are more likely to generate acid rain. So we definitely do not want high sulfur content for both of those reasons. And because those are both very big reasons, companies are now mandated before you sell oil for combustion to remove the sulfur. So the more sulfur you have present, the more expensive it's going to remove. And uh, because sulfur does have a tendency to essentially degas in the form of hydrogen sulfide, we tend to call this sour and will smell is much more likely to smell of rotten eggs. So again, you will note that that the exact sulfur content is whether it's called sweet or sour is going to be dependent on the gravity. And one of the reasons why is even if I have a fairly low sulfur content, if my gravity is fairly high, or also is my API gravity is fairly high, what this means is that in a molar ratio basis, I'm still much more likely to have a fair bit of sulfur because again, the sulfur weight is being kept constant, but the but the number of moles of gas are going to be changing. So again, one of the important things to remember is that every oil deposit is going to have a slightly different chemical makeup, and this is going to greatly affect their values. So for example, some of the most premium blend is called Malaysian uh, sweet Malaysian crude. And this tends to be very light, a lot of those small molecules we like, and has very little sulfur content, almost none. However, some of the Mexican oil from the Yucatan Peninsula tends to be much more heavy and sour, and you'll probably find Canadian oil sands sitting way out here. It essentially only becomes very profitable under high oil prices. But because both of these indicate different compositions, both in terms of carbon chain length and how much impurity I'm going to have to remove, each one of these oils will have to be processed slightly differently. And you're often going to build an oil refinery to target whatever specific oil type that you expect to come in. And again, in general, high hydrogen and low sulfur contents are going to be much easier to process, and they're typically going to be worth much more. Heavy sour, you're going to have to process it a lot more. You're going to get less valuable product coming out, so they tend to be worth less. Now, one of the other things is that we can't just describe our systems based on heavy and light. We often need to describe the individual components that make up the system. So unfortunately, it tends to be that chemical industry has their own set of language that they use to talk about carbon species that's been very much built up around the petrochemical industry. So, for example, if I'm looking at an alkane, this is called a paraffin. If I'm looking at alkenes, these are called olefins. Aromatics stay the same. And naphthenes is a way to talk about cyclic molecules. And again, these are going to be non-aromatic cyclics. But the big words you're going to see me using a lot in this lecture are paraffins and olefins. So try and remember, paraffins are going to be talking about alkanes. We also have different chain lengths of carbon tend to be put to their own use. So if I've got C4 or less, so these are methane to butane, these tend to make natural gas. They tend to be formed, they'll tend to naturally be released under atmospheric pressure. And these are going to form your classic natural gas species. When you're C5 to C10s, these are going to be a lot of your chemical solvents, such as hexanes, and these also tend to make fairly good gasoline. Kerosene eats up this middle area of C10 to C16. This also makes pretty good jet fuel. Your classic diesel is made up of C16 to C30, so much more heavy carbons. Fuel oils, which is what's often used in, say, something like a factory or on a ocean-going cargo ship, where you can have a much bigger combustion engine, tend to be much heavier. But at this point, you're also getting into a lot of your lubricants. And by the time you get past about 50 carbons, these are going to be a lot of inert species, much more carbon, very little hydrogen. Asphalt, tars, waxes, uh, a lot of physical recalcitrant species. And again, we're going to be talking about most of these species based on their use and their class. Now, which ones are we going to care about the most as essentially chemicals? So as chemists, we often like to use smaller molecules with a good handle on it. So as chemists, we tend to really appreciate our smaller olefins because we love a good alkene. I can process that very readily chemically. And I like it to sit somewhere in between about C2 and C10, as this is going to give me a lot of flexibility in how I build my molecules and put them together. However, if you're interested in gasoline, these are often going to be made of paraffins and aromatics with a little bit of olefins, and they're going to be sitting somewhere in between the C5 to up to maybe C12. But C5 to C10 is perfect. And one of the reasons why is smaller molecules can essentially be compressed more. And whereas if I try and compress diesel to the same extent, it may start auto-igniting and then I have engine knocking. In comparison, with diesel, you want it to combust under compression, and so you're going to want these longer straight chain paraffins. These tend to have much higher energy densities, and we care much less about the compressibility at this point. But the issue is that, as you may notice, each of these classes tends to be put to different uses. So I don't want to exactly have them all together. I'm going to want to be able to separate everybody out. And this leads me to the question of how can I best separate out all of these species? Well, not too surprisingly, especially when we look at chain length, these are all going to have very different boiling points. And again, their classes will also modify them. Paraffins will tend to have slightly higher, slightly lower boiling points for their pressure. Olefins will have slightly lower. They'll tend to essentially evaporate a little bit easier. This is classically seen as with aromatics, which tend to be much more volatile than their straight chain components. For example, benzene tends to be a lot more aromatic or volatile than hexane. So if we've got different boiling points, one of our best tools tends to be distillation. And typically what you'll make use of is fractional distillation. And you're going to separate out the species based on boiling ranges, which tends to also separate them out based on chain lengths. Gases coming off at the top, naphthas, which forms a lot of our gasoline, kerosene, which is also our fuel oil, or which is also our jet fuels, then diesels and fuel oils, and then working our way down. And in each case, all of our volatile vapors tend to go up, all of our heavy liquids tend to go down, and we pull out a little bit of the liquid at each level. And at the very bottom, you're essentially just pulling out non-volatile asphalt. And this gives us most of the separation we need with fairly decent purity. However, if you want to go ahead and separate out the system a little bit more, you can essentially take all your asphalt down at the bottom. So this is anything that is still fairly liquid at 400 degrees C. You'll pull it out and you'll try and pull out some of your lighter components under vacuum distillation. So the idea here is that in our first column, we're operating under 1 atm of pressure. In the lower column, we apply a vacuum pressure, which tends to make the lighter components a little bit more likely to vaporize. And you can use this to help improve separation. And at the very bottom, you're pretty much just pulling out asphalt. So have fun surfacing your road with the byproduct. Now, when you put these two distillation columns together, this is pretty much the simplest form of of oil processing that you'll find at a refinery. And this type of plant would be called a topping facility. So you separate it out twice, you package up the individual components and sell them. Now, this process tends to have two very big shortcomings. The first of which is that I still have a whole bunch of impurities in each of these in each of these levels, which means that I've got a whole bunch of sulfur, nitrogen, and oxygen sitting in my gasoline and kerosene. For this reason, you won't see many topping facilities anymore because in most countries they tend to be illegal because they have toxic amounts of these impurities. Similarly, you're very much limited by what your original composition is. What you bring in is what you get. And so historically, a topping facility was plenty good as you'd be able to sell most of these species in these ratios, and you tended to be much more likely to be using light sweet crude, which was a lot of what the original generation of oil fields would generate. However, as time has gone on, we have a lot more heavy sour. So we need ways to essentially remove our impurities and help improve our distributions. So one of the first and most important things is that we've got to remove those impurities. This is by law, and it's also an environmental mandate. They must be removed. So we have to try and remove the sulfur. However, if you try and remove the sulfur straight from the crude oil, it's going to be really hard. So instead, what we try and do is we try and remove the sulfur from the fractions that essentially can do the most, it's most likely to be present and most likely to do the most damage. So for example, it's not going to be that important to remove sulfur from our natural gas, as there's going to be very little sulfur present there. It's also going to be much less important to remove sulfur from, say, our fuel, from our industrial lubricants and our asphalt, because it, again, won't do too much damage there because most of the sulfur will be bound up in a recalcitrant form. Where it's really going to be important to remove the sulfurs from these mid-ranges. So specifically our naphthas, so this is going to be our gasoline, our kerosene, and our diesel and fuel oils, because these are going to be burned and they will release sulfur oxides and hydrogen sulfides, which can do a lot of environmental damage. So now I need to figure out ways to remove sulfur from these streams. So one of the simplest ways we can do it is called hydrodesulfurization. This is often met with the colloquial name of sweetening, because we take a sour crude and we make it a sweet crude. And this can essentially be done by treating whatever the oil stream that we're looking at with hydrogen gas at fairly high temperatures and over a catalyst. Classically, this is some sort of molybdenum catalyst, either mixed with cobalt or nickel activating agent. And this is typically going to be done in a fixed bed reactor. So essentially, you're bubbling the hydrogen and the oil up through the solid catalyst. So this is then going to generate a series of products that we can remove via gas stripping. So essentially, you'll put it through some form of water or other liquid where we're going to essentially be able to pull out the lighter gases. And so we can look at what happens for each of the individual components. If I have, say, a sulfur impurity, we can imagine this as a sulfur-based ether. When we treat it with 2 equivalents of hydrogen, we generate hydrogen sulfide and essentially truncate the associated carbon group. And then again, we can use gas stripping to pull out the hydrogen sulfide. And a very similar treatment for removing oxygen and the nitrogen. And again, the 2 most important ones here is the sulfur for its toxicity, and also, interestingly enough, we get the ammonia as a bonus. And this is very important because nitrogen-rich fuels can also tend to cause a lot of damage to metal components. So being able to get these two removed are going to be very important. However, one of the unfortunate parts about this sweetening process is that it tends to need a source of hydrogen. So we need to go ahead and hunt down a hydrogen source. So you could theoretically grab the hydrogen from, say, something like hydrolysis of water, but that turns out to be a little bit more expensive. And it turns out you've got plenty of hydrogen present in your refinery. So what you're typically going to do is try and pull hydrogen gas from the least valuable product streams. And traditionally, the two least valuable product streams has been natural gas and our lower distillates. Now, natural gas is going to be a great source because by its very nature, it's going to be very hydrogen rich. However, some places will pull the hydrogen from essentially our heavy naphthas. However, one of the things worth noting is a lot of the heavy naphthas, by their nature, will have a much lower hydrogen ratio, so may not be the optimum target for hydrogen for removing hydrogen. However, we'll go ahead and look at both of these processes as they're still both fairly widely used. So starting with taking a look at our straight chain paraffins, so you can use what's called catalytic reforming. So you're going to take a lot of your long chain paraffins, which tend to make very poor gasoline. They cause a lot of engine knocking and maybe a little bit have some poor ignitability. So essentially those that may be a little bit too short to make good diesel or kerosene. And then you'll essentially run them over a catalyst at high temps, and you'll essentially form a smaller molecule, oftentimes an aromatic, and a lot of hydrogen. So typically the catalyst here is going to be some rhenium-based catalyst, and again, at high temperatures. So the typical products here are going to be the hydrogen, which we're naturally going after, but also you're going to get some mix of olefins, paraffins, and aromatics. Now, one of the reasons why this is quite nice is that, again, olefins have great chemistry, and a lot of our branched paraffins also are going to have good properties as gasoline, and it turns out aromatics tend to have very good properties as combustibility properties for gasoline as well. So you took one not so profitable species and you turned it into two profitable species. So this is perfect. But in truth, most of the hydrogen tends to come from what's called steam reforming. So you take either your light gas stream, or you go ahead and purchase natural gas from a manufacturer, and then you run the natural gas along with some steam over a nickel catalyst at fairly high temps. And again, high pressures of steam to help drive the reaction to the right. Now, when you do this, you'll generate carbon monoxide and hydrogen. Now, because it turns out most people don't want to produce carbon monoxide, you can go ahead and then process that a little bit further at essentially a slightly lower temp over a slightly different catalyst. It's often a copper zinc aluminum alloy, alumina alloy, to produce CO2 and hydrogen. However, it is worth noting that sometimes you will take the carbon monoxide and hydrogen and sell this as syngas, where it's possible to take your natural gas, turn it into syngas, and then using Fischer-Tropsch synthesis, reform this as essentially diesel oils. However, this is typically only done in countries with low quantities of oil fields and a high demand for diesel. Then you're typically going to be removing the hydrogen using a zeolite filter. So a zeolite is essentially highly structured clay, which we'll talk about a little bit more later. So if this is all you end up doing is essentially removing the sulfur and taking a little bit of your oil and making a little bit more diesel and kerosene, this is called a hydroskimming plant. So these plants are still fairly common in Europe. One of the reasons why is Europe tends to use a lot more diesel. But in the US, these are typically seen as lower value. And so we'll typically need to do a little bit more processing. So in order to try and turn a little bit more of your diesel and your fuel oils into the more profitable gasoline and lighter species, we're going to need a little bit more upgrading. So the next major method is called fluid catalytic cracking. So a lot of people when they say cracking, are talking about this FCC process. So one of the things that makes this a little bit different is you'll notice that there is no hydrogen as an input or an output. Instead, what we're going to be doing is we're taking, again, our long chain parafilms, and then we're going to use high heats and, again, alumina silicates, and we're going to essentially isomerize or crack these long chain carbons. So this will gonna generate a mix of species. So either you can cause an isomerization of your long chain carbon to make a uh, branched species, which tends to make very good high octane fuels. But you can also tend to cause some breaking where you're going to make an equal amount of a short chain paraffin, which can, again, be more likely to be used in one of these industrial chemistry processes or in gasoline. And then you're going to also make some olefins, which, again, are much more likely to be used as gasoline, and again, are also much more useful as, say, a precursor for making plastics. And so, again, this process is very good for the generation of our gasoline and industrial chemical feedstocks. However, when we're saying alumina silicates, what we're often talking about is zeolites. So zeolites are essentially a silicate or a clay-like structure with some alumina impurities, which can then interact and cause the catalysis. Now, one of the things that makes zeolites different from most silicates is that they tend to have these channels or pores that travel through them. And these pores are often of very specific length, so that they're only going to allow molecules below a certain size to readily exit. So, not too surprisingly, this is a very good process for taking a large molecule and turning it into a smaller molecule, which can really help increase uh, product selectivity. Not to mention, these channel sizes also give us a much higher surface area and thus a much higher catalytic rate. However, not too surprisingly, because of the nature of these small channels, they are vulnerable to what's called coking. And this is essentially a buildup of a solid carbon species on the surface, which will essentially block the channels and then eventually kill the system. It is worth noting that coking can often be fixed by treating the system with concentrated hydrogen at high heats, but as you may have noticed, that's only done when necessary, because in general, we already put a lot of work to try and get our hydrogen in the first place. So one of the other variants, again, to this fluid catalytic cracking is to instead change our catalytic surface to nickel and add in a little bit of hydrogen. So again, at this point, we're taking a lot of that hydrogen we already generated for hydrotreating or hydroskimming, and we're going to use that to drive the cracking. So now, instead of producing olefins, we're much more likely to produce our smaller chain paraffins. So one of the reasons why the hydrocracking tends to be used a little bit more is with increased regulations, we're wanting to drive down the amount of aromatics, as these can be carcinogenic species. In addition, this will also act as essentially a way to remove the sulfur and nitrogen from the mixture all in one quick go. And so again, this is going to be a little bit more common when you're making kerosene and diesel, which tend to like the straight chain paraffins a little bit more than in gasoline production. However, now we just produce a whole bunch of light gas. And sometimes you may have produced too many small chains. Not to mention, you may have just more natural gas than you know what to do with, and you don't want to turn all of it into hydrogen. So one of the other things you can do is take the stuff that's a little bit too small to make good oil and perform what's called alkylation. So what this essentially does is you're combining a mixture of your olefins with some of your paraffins in the presence of an acid catalyst, and you're essentially going to cause these mixed and highly branched species. So these this alkylation process is really good at making highly branched species like isooctane. And isooctane, which you see here on the right, is the very definition of an octane rating. So when people are talking about octane rating, it's essentially you burn like a mixture of what percentage of isooctane. This is one of the best and classic fuels that you want to compare to. And not too surprisingly, this is also a fairly common form of catalytic upgrading with essentially the highly valued nature of gasoline production. So if I'm making use of any combination of FCC, hydrocracking, and any of the other upgrading techniques we've already covered, this is called a conversion plant. And this is essentially one of the most common types in the US. So essentially when we've done, by doing this deeper conversion, what we've done is we've specifically targeted generating gasoline in this C5 to C10 ratio. And again, this same area can often give us a lot of our same chemical precursors, but maybe a little bit more rich in something like in our olefins. However, there's one chemical stream that we haven't really tackled. So we've really talked about how we can take our fuel oils and turn them into gasoline. And we've talked a lot about how we can take our natural gas and turn it into gasoline. But what we haven't talked about at all is how we can essentially treat our bottoms. So this is a lot of our bitumen and asphalts. So what we can do is take our heavier products, so starting with our fuel oils and working our way down, and try and improve their current value. And we can often do this via vice braking. So vice braking is essentially another form of thermal cracking. So again, kind of like our FCC process, except for one of the major differences is we're going to have to use much higher heat, and often we're going to do this over short periods to prevent essentially denaturing of our species. And because of these high heats, it often occurs uncatalyzed. So what we're going to do is we're really going to take a lot of our fuel oils and essentially boil off any amount of hydrogen that's present. So this is going to typically leave as hydrogen, natural gas, and gasoline. And what we're left with is kind of a very unnatural, very heavy fuel oil, bitumen, and asphalt. So not a lot of really good things. However, sometimes this isn't going to be enough for some places. So they'll give up on making asphalt at all, and they're going to increase the temps and retention times even higher. And you can really improve the quality of your light species at this point, though at the end you start making a lot more diesel because you've stopped generating any hydrogen. But on the downside, it comes at the cost of having removed almost all of the hydrogen out of your bottoms. So at the end, all that you're really left with is often called coke. So coke is essentially pure amorphous carbon. There's almost no hydrogen left. And as a consequence, the thing that it's really best for at this point is going to be metallurgy. So if I'm, say, making steel, I need a pure source of carbon, and coke can be actually fairly good for that. It's also a good precursor for making carbon electrodes, which as an electrochemist, I'm in favor of. However, there's also an unfortunate side effect of this, is that traditionally, coke was often used as a low yield fuel source. So it's very bad as a fuel source because all you can do at this point is turn carbon to CO2. One of the biggest problems is that almost all of our impurities have now been centralized in our remaining coke. So it's very common that they have high concentrations of species like arsenic. And this can be quite problematic because as soon as you burn it, you can generate a lot of very dangerous pollution. And this is one of the biggest reasons why it's currently forbidden in the US. However, an unfortunate number of companies, like the Koch brothers, do try and sell the coke they produce overseas to poorer countries to essentially try and maximize their profit under the environmental damage of others. So again, this is one of the things you have to watch out is some people will try and cut corners. So If I take my normal conversion plant and I add in some form of vice breaking or coking, I generate what's called a deep conversion plant. So this is really trying to milk everything we can out of the system. And these typically only tend to exist in the US, where we're really trying to get the most out of our oil. However, you will notice that this is about as complicated as oil refining can get, and it will involve pretty much every type of process we've talked about so far in more or less one of the mother of all uh, process diagrams. However, we can take a step back and learn a couple of major lessons from our petroleum refining. First, one of the important things I like to mention is that when done properly, it's possible to use every part of a chemical resource, and you don't let anything go to waste, whether it's essentially as natural gas or even as essentially asphalt for road tar. You can find a way to put everything to use. So if you do have to use oil, you can at least make sure as little of it's going to pollution as possible. And one of the other things, and this is fairly uniform, if something has a low value, you might be able to transform it into something else. But in a similar sense, one of the things I like to comment on is environmental regulation. And one of the biggest demonstrations of this was the change from topping uh, to these conversion plants. Because one of the things that enabled this this conversion was essentially the banning of sulfur-rich gasoline. No company wanted to invest uh, in the new machinery to go from topping to hydroskimming to conversion. However, as soon as the policy went into effect, you may as well build the plants that not only uh, are generating or removing the possible pollutants, we're now taking that sulfur and we're turning into sulfuric acid and other uh, useful and sometimes profitable chemical species. And so sometimes uh, adopting environmentally friendly practices are going to be for the best long-term advantage of the industry, but it's often going to take some kind of regulation to get the change started. So again, when a lot of people complain about regulations, it's often at the cost of short-term profits, but well-crafted regulations can often drive long-term innovation and profitability. So next time, we're going to essentially take up where we left off by focusing in on one specific substream of this production. We're going to try and put that ethene we just generated to good use and make some plastic. Till then, take care.